I don't know what it means.
I don't know either. I just played Tony Hawk.
And they do inverts in Tony Hawk. Well, so what is the character doing when they do it?
I can't remember.
So maybe is it where they go upside down? If you invert it,
They definitely don't go upside down.
they don't go upside down. When they do flips, they don't go upside down, or they only go like sideways. Yeah.
Maybe the board goes upside down, I think. Maybe the
Oh, flip the board. Maybe that might be it. All right. Apparently we don't have safe version. That's okay. So when we do inverses of functions, we're going to be flipping the x and the y. So we're going to be inverting your domain and inverting your domain and range back and forth with one another. So really quickly, well, we don't even have to do this because we did that. So just go back. Don't even write this. We did this in our warm-up. How do I solve that for x? Subtract 4, divide 2 would be your inverse operations, right? When you solve equations, you do inverse operations. We subtract 4, we divide by 2. The inverse of plus 4 is minus 4. The inverse of multiply by 2 is divide 2. So when we start talking about inverse functions, all we're doing is focusing on an ordered pair. And the inverse would be changing the input and the output to turn into the output and the input. Or, it makes more sense to think about it, the inverse of xy would be y comma x. So, given the ordered pair, x comma y, the inverse would just be switching your x and your y. So whatever was your y value there will become technically your new x term in the inverse. Whatever was your x term in the original will technically now become your y in the inverse. Okay? So if we think about this, we know that all x values represent the domain. So the domain of the regular function will now become the range in the inverse. The range of the original function now is going to become the domain. That's what we have written under the blocks. The domain of the inverse is the range of the original relation. So the domain of the inverse is the range of the original relation. And then vice versa, the range of the inverse is the domain of the original relation. All right, so let's practice creating an inverse. We're going to start with a really easy one. It's going to be a set of ordered pairs. And what do you think we're going to do to make the inverse? You got it. Is everybody ready?
Yeah.
All right, so example 1. Here is our relation. The set of 1, 2, 2, 4, 3, 6, 4, 8. So the first question we have to ask ourselves, is this relation a function?
Yeah.
How do I know it's a function? Bless you. Well, that would be more specific to linear.
Yeah.
Sarah? No repeated x terms. Perfect. This is a function. We don't have repeated x terms in our order pairs. Okay. So now, let's do the inverse. What would be the inverse of this function? What would be the first ordered pair?
2, 1.
2, 1. What would be the second ordered pair?
4,
4, 2. There it is. I know this is where we find those who have dyslexia. Sometimes I have dyslexia. Next one would be 6, 3, and then 8, 4. Is the inverse of this function also a function?
Yeah.
Yeah. This is also a function. Can someone think of an ordered pair that I could add to the original relation to still keep it a function, but make the inverse not a function?
12, 8.
So if I add it 12, 8, we still have a function up here, right? But if I do the inverse of 12, 8 down here, it becomes 8, 12, which no longer is a function. Okay? So it's really easy to find inverses when you're given an ordered pair. What would be the domain of our original function?
1, 2, 3, 4.
1, 2, 3, 4. What's the range?
2, 4, 6, 8.
What's the domain of my inverse? What's the range?
1, 2, 3, 4.
Right, so we're just flip-flopping them. Okay, got that? So now what happens when we actually have an equation? So if you have an equation y equals 3x minus 2, and we need to find the inverse for that equation. Let's think about this graphically first. What kind of shape does that make on a graph? A line, right? A diagonal line. What would be the domain of a diagonal line? All real numbers. What's the range of a diagonal line? All real numbers. So if we find the inverse, what should be the domain of the inverse?
All real numbers.
And the domain of the range,
All real numbers.
or the range of the inverse would be all real numbers, right? So that means the inverse should end up being another linear equation. Okay, so what did we do previously to make the inverse? We switched the x and the y values. Well, now I don't have x and y values. I literally have an x term and a y term. So I'm going to switch my x and my y term by turning my y into an x and turning my x into a y.
What about the
And then I'm going to bring down minus 2. There it is.
So that would be the inverse.
So that is the inverse. But for us to make sense of this, we should turn it into slope-intercept form, right? So can we turn this into slope-intercept form? Get the y by itself? How do I get the y by itself? First move would be to add 2. So I would get x plus 2 is equal to 3y. Next move, divide by 3. If I wanted to make it look good, what would it look like in slope-intercept form? What would be my slope? Well, what's the coefficient in front of the x? 1. So it really would be 1/3 x plus 2/3. So that would be the inverse of our original problem. Okay.
Do we always have to take it to that
You will always have to need to solve it for y. The book will sometimes have it looking like this. If you look up your answer, they'll keep it maybe sometimes x plus 2 over 3. It depends on what they're looking for. You'll see it both ways. Okay? If you have your calculator out, pull out your graphing calculator if you have it. I want you to go to your y equals screen. And I want you to type in the first equation, which was y equals 3x minus 2.
Wait, how do you do that?
X is the
So at your y equals, this button right here is your x term. So I type in, so y equals 3x minus 2. And then what was the other one?
1/3.
1/3.
X.
So if I wanted to do a fraction, me personally, because I grew up with 83 calculators, I used parentheses to show my fractions. Some of the 84s, remember I showed you that alpha and then y equals, which gets you that little fraction symbol. If you like that, you can choose that you want it to make a fraction. Either will work. So 1/3, that x, and it was what? Minus plus 2/3? Plus 2/3. And then do a zoom 6, just to go to a standard 10 by 10, 10 by 10. And then it should graph both of our lines for us. So let's focus on this graph. What do we notice about, what's this point down here? Yeah, the coordinates would be what? I'll make it purple. 0, comma, -2. What would be the inverse of that point? Is that on the other graph? Yes, -2, 0. What would be, let's pick another good point. Look at this point here. What's that coordinate point? 1, 1. What's the inverse of 1, 1? Is that on the other graph? Yeah. What's another good looking one? If we do, is there anything that's nice? I can find nice points by hitting trace. If I do -6, I get, ooh, -620. That's way up there. I'm not going to be able to get that. If I trace +6, what do we get? That's still going to be out there. If I trace +3, 7. There we go. So 3 7's on there. What will be the inverse? 7, 3. So if I hit the down arrow, and you guys can do the same thing, it'll jump you from back and forth between the two lines. I hit the down arrow and type in 7 for my trace. It comes up 7, 3. So what would be the line, if we go back to geometry, what would be the line of symmetry?
In between the two.
What would be the equation of this line of symmetry, do you think? Well, right here is the point of intersection, right, where they were the same. And then it's kind of reflecting here, reflecting here, reflecting here, reflecting here. So is our line of symmetry, is it going to have a positive or a negative slope? Like if I folded it over the line of symmetry, this would match up with this. Am I losing you guys? Right, so if I sketched this line, can we see how if I fold it on that line, that would match up with that? That would match up with that. That would match up with that. What would be the equation of that line? It would go through 0 and have a slope of 1. So it would be y equals x, right? Thank you, Brandon. All right, but anyway, so given a graph, would you be able to graph its inverse? So if I just gave you this one graph, so I went up here, took away this plot, I went back to the graph, would you be able to come up with the graph of the blue line?
Yeah.
Yeah, by doing what?
Using the points.
Finding some points. So like we chose this one down here was 0, -2. The inverse of that is -2, 0. Here we chose 1, 1. The inverse of that is 1, 1. All you need is 2 points to make a line, so that would be the inverse, which was pretty close to what the red graph was, right? Okay, back to our notes. So try this one on your own. So if we had y equals -5x minus 7, what would be the inverse equation? So do exactly what we just did, and then put it in a slope-intercept form, because that's what makes the most sense for us. catch up with you.
You don't have to graph this, right?
No, you don't have to graph it, just rewrite it. So I'm getting negative 1/5 x minus 7/5. Do you guys agree?
Yeah.
Okay, try one with a fraction in it. Y equals 2/3 x minus 5. What would be the inverse?
Minus 5. That's correct. No? X equals 2/3 or fifths.
All right, so I got to that spot with multiplying by the reciprocal on both sides. But when you multiply by the reciprocal on both sides, you need to remember to multiply everything by the reciprocal. So it would be 3/2 x plus 15/2 equals y. Okay, so be careful of that. If you have this fraction, to get rid of it, you multiply by the reciprocal, but that means I need to multiply the x by 3/2, and I need to multiply the 5 by 3/2. Okay, and fractions are A-okay. Okay, so given a set of ordered pairs, could you come up with the inverse? Yeah. Can you identify the domain and range of each?
Yeah.
Given an equation, can you find the inverse?
Yeah.
So now all we're going to do is turn it into function notation. We're not going to do any of those. So we're going away from equations to functions. Same exact thing, it's just the notation is different. So the most important part here that you're going to get out of this statement, it says if a function f and its inverse are both functions, the inverse of f is denoted by, and here is your new notation over there on the far side. That was pretty, I need to make my transparency a little bit better here. Doesn't want to get any farther than that. Oh, what does that do? Oh, nope, don't want that. I don't know. Okay, so this notation right here, whenever you see F2 or G2 or H2, the -1 power, we're not talking exponents here. We're not talking taking it to the -1 power and then shifting it down into the denominator to make it positive. That notation right there means we're saying the inverse of function f. Okay? You can do the same thing for y. In those previous problems, we could have said the y inverse is equal to, and whatever the number is. So if you're looking for an inverse and you see this notation, that means it says it's looking for the inverse. It's not something to a -1 power. That's not an exponent. All right, so if I wanted to find the inverse of f of x equals x to the 3rd power, how do we do that? Well, what did we say f of x is the same thing as? A y. So what I would do is I would just turn that into a y equals x to the 3rd. So now what do we do to find the inverse of that? X equals y to the 3rd. Good. How do we undo a 3rd power? Cube root. Yeah, take the cube root of both sides. So then we get y is equal to the cube root of x. Okay. Now, if you stop there, I'm not going to take points off. I'm not going to be picky about it. But you technically should then reconvert it to function notation, which would give us the f inverse of x is equal to the cube root of x. And that would be your final answer. Okay? So, if you see that notation, that just means inverse. You just do the same thing. You just turn your f of x into a y, do exactly what we've been doing, and then just remember to turn your answer back into function notation. Okay, so given, what would be the domain of that? What was our domain here? Can I put any number I want in place of x? Yes, there's no restrictions. What's going to come out as a number? Can I get any, bless you, can I get any possible number as an answer? Yeah, technically. I could cube any number to get any other number out there. There's an infinite number of numbers that would come out as resulting of cubing something.
Every number.
Sure you could, with decimals. Technically you could. We're not going to spend our life's work doing that. So if my range can come out all real numbers, what would be my domain down here?
All real numbers.
All real numbers, right? If my range is all real numbers here, remember your inverse is domain is the same as the original range. If I turn this into a squared, could I put any number in place here? Yes. Will I get every number coming out?
No.
Because if I square a number, I won't get what specific numbers?
Prime numbers.
I mean, we could get prime numbers.
You're not gonna get
If you square something, what will you never get as an answer when you
One.
square it? You can get 1. 1 squared is 1.
0.
0 squared is 0. You never get what? Negatives, right?
Oh, yeah.
I can't get negative numbers. So my range up here is all numbers larger than or equal to 0, right? So my domain down here, if this was a square root, would be what? X needs to be greater than or equal to 0. Because I can't have a negative number and take the square root of it, right? Yeah, maybe? All right. So, looking at a graph, or looking at a set of ordered pairs, we can find the inverse. Looking at either an equation or a function, we should be able to find the inverse. So now, how do we determine whether a graph has an inverse?
What was the domain?
Oh.
X is greater than or equal to 0. So we had the vertical line test to tell us whether a relation was a function. Now we have what's called the horizontal line test. And the horizontal line test tells us that the inverse of a function is a function. Bring some geometry into our life. Biconditional statement right there. If and only if every horizontal line intersects the graph of the function at no more than 1 point. First graph. Is that graph a function?
No.
Does it pass the vertical line test?
Yes.
So
No.
this is a function. It passes the vertical line test. Would its inverse be a function? No. The inverse is not a function because it doesn't, I'm gonna run out of room, doesn't pass you got it. Doesn't pass the horizontal line test. Because I can draw a horizontal line, and does that intersect more than one place?
Yeah.
Yes.
That's a straight line.
That was a pretty good line. Yes, I admit that's pretty good. Usually I don't do very good. So the inverse is not a function because it doesn't pass the horizontal line test. What would the inverse look like as a graph? Can you envision what it would be? Would it be upside down? So let's say this is at 0, -2. The inverse would then be at... So that means the bottom of my parabola is now going to be here. Yeah, it's going to look like that, right? Which shows that would not be a function because it would not pass the vertical line test. All right, so we're just going to go through a series of these. You don't have to try to get these written in your notes. Is this a function, yes or no?
Yes.
The original is a function, passes the vertical line test. Would its inverse be a function?
No.
No, because it would not pass the horizontal line test. If I needed to graph the inverse, this point is at -2, 3, so that inverse would go to what? Yeah, so if this is at -2, 3, then I would graph it at 3, -2. What's another point?
1, 0.
1, 0, or 0, 1. So the inverse would be at 1, 0. This is at 1, 2, 3, 4, -5, 0. So 0, 1, 2, 3, 4, 5. So what's happening here? It's going like that, right? Kind of funky, huh? Would this graph would the original graph be a function?
No.
No. Would its inverse be a function?
Yes.
Yes, because it would be up there like that. We already did that. Would this original graph be a function?
Yes.
Yes. Would its inverse be a function?
No.
No, because this little area right here would not pass. Would that be, is this original one a function?
Yeah.
Would its inverse be a function?
Yeah.
Yes. Is the original one a function?
Yeah.
Is the inverse a function?
Yeah.
Yes, it would be. If it was a complete parabola down, then it wouldn't be. All right, so the last thing we have to do is a way to verify. Don't even worry about writing this. Let's just do an example. If we incorporate composition of functions with inverses, we can verify that two functions are inverses of each other by doing a composition of the two functions. So if I have function f, that is 7x minus 2, and I have function g, which is 1/7 x plus 2/7. I want to see if they are inverses of each other. Now technically we could just find the inverse of this. To find the inverse of this, we would do what?
Set it equal to 1.
Right, and then we would add 2, and then divide by 7 would be our inverse operations. So we could easily just find and say, hey, it is the inverse, they're the same things. But we can do a test using compositions of functions, which is what the book is going to ask you to do. So can we do f of g of x? We can. It might not be that pretty, but we could do it. So if I put the g function into my f function, what would that look like? 7 parentheses, and 1/7 x plus 2/7 minus 2. Simplify that. What happens when you distribute the 7th to both those terms inside the parentheses? It's going to be 1x NA plus 2 minus 2. Keep going. Simplifies to x. Good. Now let's do the opposite. Let's do g of f of x. So now I'm going to take the f function and put it in place of the g function. So now I get 1/7 times 7x minus 2 plus 2/7. Distribute. Well, 1/7 times 7x is x. 1/7 times -2 is -2/7. Plus 2/7 would go to x. What do you notice?
They're both the same.
They're both the same. And if any two functions are inverses of each other, they will always end with an x when you do the compositions of them. Doesn't matter what the functions are. If these guys are inverses of each other, when I do the composition of them both ways, it will simplify to an x. Doesn't matter what the function is. Okay? So when you're asked to verify if two functions are inverses of each other, you have to do the composition both ways. Okay? If it works one way, it's probably going to work the other way. So make sure you're doing your arithmetic right. But you have to do the composition of them both ways. Okay? All right, let's have you try one and then we'll be done. Let's do this one. So there's your f, there's your g function. Verify that they are inverses of each other. Yeah.
Can I go to the bathroom?
Yeah, just sign up. You have to do f of g, and then you have to do g of f. It's going to be your most tedious problems.
But they're all gonna be like that, right?
No, there might be some that have like x plus 1. Like if I change that to a plus 2, if this originally was x plus 2 instead of x minus 2,
Yeah.
then it would have been, oh, hold on, that's not right. I didn't do my math right.
That's -4.
Yeah. Oh, that's supposed to be a plus. That's what I did wrong. Right? Yeah. So if this originally would have been a plus 2, then I would have been left with 5x plus 4, which doesn't simplify to x. So then they would not be inverses of each other. Okay? All right, so for your